At 35,000 feet, a commercial cabin is a masterpiece of curated tranquility. The lighting is soft, the hum of the engines is distant, and the air is perfectly still. Then the descent begins. That peace is replaced by sudden mechanical violence. Cabin panels rattle, intermittent whirring groans through the floorboards, and heavy thuds vibrate through the seats. For most passengers, these physical forces feel like the precursors to a catastrophic failure. Without the technical context, the sheer volume of the aircraft's deceleration feels chaotic. Transitioning a 70-ton machine from the sky to a concrete runway requires a sequence of high-pressure mechanical events, beginning several miles before the wheels touch the ground. The first sign of the landing sequence is often a heavy, metallic bang that reverberates through the entire airframe midway through the descent. This sound marks the moment 3,000 psi hydraulic selector valves fire in milliseconds. They provide the force required to release the mechanical uplocks that hold the heavy landing gear inside the fuselage. Once the locks release, the gear drops into position around a central main beam and trailing link. The primary shock strut here, a cylinder of nitrogen gas and oil, is extending, preparing to absorb the landing's kinetic energy. The roaring wind that follows is the result of turbulent air rushing into the newly opened wheel wells. At 200 miles per hour, the cavity in the fuselage creates a massive amount of aerodynamic drag and noise. This sequence isn't a malfunction. It is the sound of the aircraft extending its most robust defensive structure against the coming impact. The second major shift occurs the instant the tires strike the tarmac, bringing a violent, stuttering vibration that feels as if the aircraft is struggling to maintain its grip. This happens because the physical compression of the gear closes a gap in the weight on wheel sensors. These sensors transmit a ground status to the flight computers, authorizing a total change in the aircraft's behavior. This signal allows the transition from flight mode to ground mode, which immediately activates the carbon multi-disc brakes on the main wheels. The stuttering you feel is the anti-skid control unit. It independently modulates hydraulic pressure to specific wheels thousands of times per second, preventing the tires from locking up and blowing out on the high-friction concrete. The screeching isn't a loss of control. It is the sound of a computer system managing a delicate balance of pressure to keep 70 tons of metal moving in a straight line. Immediately after touchdown, the cabin is filled with a deafening engine roar, accompanied by a sudden forward-leaning lurch. While it sounds like the engines have suddenly reversed their rotation, the fans continue to spin in their normal direction. Instead, the aircraft deploys thrust reversers. Physical barriers block the rearward exhaust path, forcing the jet blast out diagonally forward. To achieve this, heavy components like clamshell doors or cascade grids slam into the airstream to redirect the airflow. This redirected thrust creates a massive wall of air that fights the plane's forward momentum, efficiently bleeding off speed without relying solely on wheel brakes. The violent shaking in the cabin is the result of raw jet power being used to neutralize kinetic energy. While these systems are vital for safety, the noise they generate has become a focal point for environmental protests and community backlash near major hubs. In response, the International Civil Aviation Organization has established new binding standards that will fundamentally change the sound of commercial flight. By 2029, all newly certified aircraft models must be at least 6 decibels quieter than current standards, representing a 30% reduction in noise levels. This is coupled with a 2031 mandate requiring a 10% reduction in fuel consumption at the point of certification. These targets are forcing manufacturers to re-engineer the violent mechanical systems of the current generation, replacing them with more efficient, silent alternatives. The rattling and roaring of the current landing sequence is a hallmark of safety in the jet age. When the floorboards shake, you are simply feeling the physical work required to bring 70 tons of momentum to a complete stop.